Here we've got steam entering a turbine that's operating at steady state. So the steady state's important here. Pressure is 2 megapascal. Temperature is 360 degrees Celsius. We've got a velocity of 100 meters per second. Now we've got saturated vapor that's going to exit at a pressure of 0.1 megapascal. Notice that decreased, with a velocity of 50 meters per second. Now the elevation of the inlet is 3 meters higher than at the exit. Now notice we have elevation here. We haven't really seen a problem like that in the examples so far. The mass flow rate of the steam is 15 kilograms per second, and the power developed is 7 megawatts. We're going to let G equal 9.81. We want to find the area at the inlet, and we want to find the rate of heat transfer between the turbine and its surroundings. So that's what we got. Now, I'm going to go ahead and write out our conditions at state 1 and 2, just so I can see them without having to redo that problem again. So P1 is going to be 2 megapascal. The temperature is 360. Velocity is 100. And what else do we know here? Mass flow rate is going to be 15 kilograms per second. Notice it just gives a general value, and that's because it's steady state. So mass flow rate will be the same regardless of if you're at the inlet or exit. So we got 15 kilograms per second, and our elevation at the inlet, let's just call it Z, we'll say Z1, is 3 meters higher than at the exit. So we'll say that the exit is our reference line, basically, and we'll measure up from that. Now, what else do we need to know here? Let's see. Let's list point 2 here. So it exits at saturated vapor. We've got that. Our pressure is going to be 0.1 megapascal, which is 1 bar. And our velocity is 50 meters per second. And we're going to say this elevation is 0, because I'm going to make the exit the reference line where I measure the elevation from. All right, and we also know our power developed, which doesn't matter which one of these you put it at. Power developed, remember, is W dot, is going to be 7 megawatts. It's going to be positive because we're developing power, not requiring power. So 7 megawatts is equivalent to 7,000 kilowatts. Alright, so now we've got all that established. Now let's get started. So part A, we want area at the inlet. Anytime you're asked to find area, you're going to automatically go to that mass flow equation, because that is our equation that has area in it. We've got rho AV, and usually we convert over to specific volume. So now let's have AV over V. Now, m dot we know, area we don't know, we're looking for that. The velocity we know, and then the specific volume, if you look, you're given this pressure-temperature combination, so we can figure out what V is from the table. So we're going to have 15 kilograms per second. That's going to equal the area times 100 meters per second. And then the specific volume, if you go ahead and look, we have steam here. So steam typically indicates superheated vapor. You always want to double check that though, because sometimes some of the problems indicate steam when it's really saturated vapor. So now we got 0.1411, that's from the table, cubic meters per kilogram. If you're using the Moran textbook tables, it's A4, is where we got that. Now you can go ahead and solve for area. Area is going to be 0.21165 square meters. Alright, so now we got that. Now, to takes care of part A. Let's go ahead and look at part B. Now we want rate of heat transfer between the turbine and the surroundings. This is the Q dot term. Anytime you need Q dot, you're going to go to the energy balance equation. So 0 equals Q dot minus W dot plus M dot. And I'm going to write out the full equation this time. So we're going to have H1 minus H2 plus 1/2 V1 squared minus V2 squared, and then plus G times Z1 minus Z2. Now usually it tells us to ignore kinetic and potential effects. It did not tell us that this time, so that means we're going to keep these things in here. Alright, so let's go ahead and go through these. H values, those will be found in the tables. And then velocities, we've got our velocities. V1 was 100, V2 was 50. And this potential term, it gave us G, and then we also have our elevations. So basically we have everything we need to find Q. We're just going to have to go to the tables, find these values here. We also have W dot, remember that was given right there. So let's go ahead and plug everything in. And just to save room, I'm going to do each of these terms separately and then we'll combine it all. Let's look at this one first. Let's do kinetic energy first. So 1/2 times the change in the squares of the velocity is going to be 1/2 times 100 meters per second, square that, and then minus 50 meters per second, square that. Now I need this to be in the same units as the other terms. So we're going to have to convert here or something. So let's look at the conversion we'll need. We're going to do 1 Newton per 1 kilogram meter per second squared. And then I want to get to kilojoules. So I'm going to have 1 kilojoule per 10 to the 3 Newton meters. Okay. Now, after you do all that, you're going to get 3.75 kilojoules, whoops, this is a J here, per kilogram. So you got that for that term for kinetic energy, and then for potential energy, which is this one, let's look at that one and then we'll put it together. Here you're going to have 9.81, that's meters per second squared, times 3 meters minus 0 meters. Again, we have to have the same units as all these other terms. So let's go ahead. I want kilojoules per kilogram. And conversion we need here, same thing. 1 Newton per 1 kilogram meter per second squared times 1 kilojoule per 10 to the 3rd Newton meters. That's going to give me 0.029 kilojoules per kilogram. And you can see with these small elevation changes, this term here is pretty small. All right, so that's why a lot of the times we just leave it out, because you have to have a pretty significant elevation change in order for it to make a big difference. All right, so now this is done, this is done. H1 values, those are from the tables. We'll plug those in when we write out the equation. So we're going to have 0 equals Q dot minus the 7,000 kilowatts plus M dot, which is 15 kilograms per second, and then multiply that by H1. H1 is going to come from the superheated vapor table, so that's going to be table A4. That value is 3159.3 kilojoules per kilogram. And then we subtract the one at H2. Now at the exit point we have saturated vapor, so you're going to go to the saturated water table and you'll look up that value there. So that'll be 2675.5 kilojoules per kilogram, and that's table A3 if you're using the same tables as me. Then after that we've got 3.75 kilojoules per kilogram. Notice the units are the same. And then for potential energy, we've got 0.029 kilojoules per kilogram. All right. So now that you see this, you can see why I was doing these crazy conversions to get to kilojoules per kilogram. Now that we've got this, if you look at your units, kilograms, those are going to go away. That's going to leave you with kilograms per second, which is the same thing as a kilowatt. So now Q dot is going to be negative 313.685 kilowatts. Notice this symbol is negative. And if it's negative, remember that means we are transferring heat between the turbine and its surroundings. So if it's negative, we're getting rid of energy from our turbine. All right, so we're sending energy due to heat to the surroundings. So that's what that negative sign tells you.